Welcome back to another fun lesson in probability. This is another topic that you've actually already been doing a little bit of so far this chapter, just naturally. It's stuff that it makes sense. And again, you've been doing it, even though we do it a different way. You've already been doing it this way for some of it. Some of it might be a little bit new, might be a little bit different, but we're going to look at it a little bit visually to see why things are a little bit different. So, we're going to be looking at compound events in this section. So, compound events fall under two events that we will see in our learning targets. We can have mutually exclusive events, so I can find the probability of mutually exclusive events, and I can find the probability of inclusive events. It's the other type. And so, first, what are these compound events? Events come in two different types. We have simple events, which consists of only one outcome, such as rolling a 2. And we have compound events, which consist of more than one outcome, which could be rolling a 2 or a 3. So already we've been looking at, all right, so rolling a 2, that's 1 out of 6 times. Being rolling, it implies dice, as opposed to flipping, which would imply coins. You don't flip a 2. So if it doesn't say anything like that, rolling means dice, 6 sides. Yeah. Anyway, so there's 1 out of 6. And here we had 2 possibilities out of 6. Well, in this topic, we're going to see how we can, instead of combining the outcomes, we could actually combine the probabilities themselves. So, and the key word here, by the way, for our compound events is or. Yesterday, when we were looking at independent and dependent, it was and. This is or. And we'll come back to that. So one of the ways we're going to be looking at this is through the use of Venn diagrams. And I found a fantastic Venn diagram right at the beginning of this section in the book. It looks kind of like this. And so I think we can all see what's going on here. And that would make for a great comment. Anyway, back to our types. We have mutually exclusive events, and we have inclusive events. Mutually exclusive events have no common outcome. Looking at it visually in a Venn diagram, there's no overlap. The Venn diagram would look something like this. Event A, Event B, nothing in common in the middle. These are very boring Venn diagrams. The only thing that might be more boring than this is if one of the circles was entirely inside the other circle. But the overlap is where they both happen at the same time. That would be what we were dealing with yesterday, which would be the probability of A and B. In a mutually exclusive event, that's going to be 0 because these cannot both happen at the same time. Examples of mutually exclusive events: rolling a 2 or a 3. When you roll a dice, it will be a 2 or it will be a 3. It can't be both. You could have rolling an odd or an even. It will either be odd or it will be even. If you're picking marbles, you could pick a blue marble or you could pick a red marble. It's not going to be a blue-red swirly. And so those are just some examples of mutually exclusive events. Inclusive events, those are not mutually exclusive. Isn't that a great definition? In other words, that there is overlap in the outcomes. The probability of both of them happening at the same time does not equal 0. An example here, we have our Venn diagram. There's overlap. We have our even numbers, 2, 4, 6. We have our prime numbers, 2, 3, 5. 2 is in both groups. So 2 would be an even number. It's also a prime number. It would be the even numbers and prime numbers. And speaking of and, this little symbol right here, we have a little bit of notation before we get into our equations. We'll start out with this thing. This little thing means and. And so we could write probability of A and B as P of A and B. Remember, mathematicians are amazingly lazy. Oh, strike that. We're efficient. If you have to do a lot of stuff, having this instead of and is very, very helpful, and that allows us to use and as a word in other places. But what the symbol is called is it's an intersection. It's where this group intersects with this group. It's where they meet. So we have a symbol for and, because and is a very long word, and so having that symbol saves very valuable time. Another very, very long word is or, and so we have a symbol that means or as well, and it's the exact same thing except it's upside down. Looks like a U. This one looks like an N for and or intersection. This one is a U. We'll get to the name in a second, but it's called a union. And it means or. So probability of A or B could be P of A union B, which is just read probability of A or B. And as I said, it's called a union. And so we can use these symbols in our definitions or in our equations. So, for example, the equation for mutually exclusive events, for event A to happen or event B to happen, we just add the two probabilities together. That's all that happens. In general, yesterday we were dealing with and. It means multiply. Or means add. So probability of A or B is probability of A plus probability of B. If we have more mutually exclusive events, for instance, we have rolling a 2, rolling a 3, rolling a 4, rolling a 5, we can add all of those probabilities together to get the intersection of or, which would be at least one of them. The or in probability is called an inclusive or, which means it could both happen. Not for mutually exclusive, but here if we're looking at rolling an even number or a prime number, if it's both, that still counts. I know sometimes, do you want fries or tater tots? And you say both, they're like, no, it's one or the other. Not in math. And by the way, both should be a thing. Having like half fries, half tater tots is awesome. If you've never tried it, do so. Anyway, back to this. Let's do an example. Let's do the probability of rolling a 2 or a 3. It's going to be the probability of rolling a 2 plus the probability of rolling a 3, which is 1/6 plus 1/6, which is 2/6, which, yes, reduces to 1/3. So earlier in this chapter, we were looking, it's like, hey, we have two different ways of making this happen. So that's 2 out of 6 total possible ways. Well, we could just add the probabilities here instead of adding them into one big fraction. Does that make a huge amount of difference in this example? No. But sometimes it does make the problem a little bit easier. And a lot of you have actually been doing this already. Over here for the inclusive ones, the equation is almost identical. We're going to add these two probabilities, but what happens if we add this probability, we're going to have 3 over 6, and this one's 3 over 6, but we've counted this 2 twice, so we have to subtract the intersection off of it. So the probability of A plus the probability of B minus the intersection because we've double counted it. So if we wanted to find this probability right here, the probability of prime or odd, we're going to look at the probability of prime plus the probability of odd minus the probability of prime and odd. So the probability of it being a prime number, I'm sorry, not prime. Wow, I have prime and odd instead of even and prime. Oh well, I guess we could do prime and odd. So how many prime numbers are there? There are 3 prime numbers on a dice. There's a lot more than 3 prime numbers, but on a dice, there are 3 prime numbers. So that's going to be 3 over 6 plus how many odd prime numbers are there? There are 3 odd prime numbers over 6 minus what is the intersection between prime and odd? Well, these are the ones that are prime and odd, so there's 2 over 6. So we'd have 3 over 6 plus 3 over 6 minus 2 over 6. I have the strangest feeling I was doing evens, and so this is going to be 1 over 6, and sure enough it is. I say odd, I was thinking even. I apologize. But 3 over 6 for even, 3 over 6 for prime, then minus the 1 over 6 for the overlap where it's both even and prime because we just counted the 2 twice. I can clarify that if needed with an accurate example there. It's horrible. Absolutely horrible. But anyway, add one plus add the other and then subtract off the overlap. We're going to look at another one like that. Add them together. Because sometimes it's beneficial to use Venn diagrams, not necessarily to put the individual outcomes, because we can see those. But if we have numbers, a Venn diagram is a great way of organizing those numbers. And I say that as someone who I hate Venn diagrams in English. I don't like them as the little graphic organizer for your thoughts. But here, it makes a huge amount of difference. It makes the problem so much easier. And then you'll probably be asked a few different questions based on it. So let's see what happens here. So we have a problem. 5 years after 650 high school seniors graduated, 400 had a college degree, and 310 were married. Half the students with college degree were also married. So there's no question here. I haven't put the question up, just a setting. And so we're going to make a Venn diagram. The first thing we want a box, because we need a total. And the Venn diagram, the 2 circles, or possibly 3 circles, won't include everything because there will be students who don't have a college degree and are also not married. And so those wouldn't fit in either circle, but they're important to the probability. And then we can draw our circles. We have 2 because we have 1 for college degree and we have 1 for married. And then the centers for both. Now we can start filling in what we know. I would recommend starting with the center. That is the biggest. If you start there, your chances of success in this problem go up significantly. So we want to know how many had both a college degree and were married. Well, we know that half the students with a college degree were married. So how many of them had a college degree? 400. Half of that is 200 goes in here. Well, if there's 200 with both a college degree and are married, how many did that leave out here with just a college degree? 400 had a college degree. 200 are here. The other 200 are here. These 2 places have to add up to this 400. One of the biggest mistakes is people say 400 here, which then says that we have 600 people with a college degree. These 2 add up to the total with a college degree, just like these 2 will add up to the total number of people who are married. We have 200 here. We know that there's 310 total. A little bit of subtraction tells us that there are 110 people married without the college degree. Right? Now, what about the people that don't fall into one of the circles? We have 200, 400, 510 people here, but we need 650 total. Again, a little bit of subtraction gives us 140 people are going to be outside of the Venn diagram in the box at large. These would be the people with no college degree and also not married. All right, now that we have this set up, that's the hard part of the problem. We can actually get to the questions. Oh, and while we're looking at this, each of these different sections is mutually exclusive. You're either married with no college degree, married with a college degree but not married, or not married, no college degree. And so each of them is mutually exclusive. The individual 4 sections do not have overlap. And that's important because that means we can just add these numbers together and put them over 650. Or 200 over 650 plus 200 over 650 plus whatever over 650. I would just add them all up and put them over 650. So, first question. What is the probability that a student has a college degree or is married? That means they have to be in either the college degree circle or the married circle or both. The overlap counts, remember. Well, so we can count. Let's see, college degree, that's 400. And then the rest of them that are married, plus another 110, is 510 over 650. The probability of a degree or married, 510 out of 650 students will either have a degree or married or both. And yes, you can reduce this. Sorry. I mentioned there'd probably be more than one question here. Once you have this set up, another question. What's the probability a student has a college degree or is not married? So we have all of them with college degrees. That's 400. And then all of them who are not married, outside of the red circle, would be an extra 140. So we have our 400 plus 140 is 540 over 650. And notice here, not married, that's the complement of being married. That's married complement. Everything inside this red circle would be M. Everything outside would be the complement of M. All right, one more. What's the probability that a student does not have a college degree or is married? So we need everything outside of the blue circle, which would be this 140 plus 110, or they're married. So anything inside the red circle, we already got the 110, but we can add the 200. And so we have 200 plus 110 plus 140 gives us 450 over 650, which, again, these can be reduced. And so having this Venn diagram as an organizational piece makes these problems much easier. And notice, once I had it set up, these ones we just had to figure out which numbers we add together, and we're done. One last thing to make things easier, using complements. Notice I spelled it correctly this time. We're not using complements, although that tends to make things easier as well. But using complements. Example, if we have a vending machine, offers 8 drinks, one day 6 employees each purchase a drink from the vending machine, find the probability that at least 2 purchase the same drink. So this at least 2 phrase is what tells us a complement will probably be beneficial, because the at least 2 means that 2 people could, 3 people could, 4 people could, 5 people could, 6 people could all purchase the same drink, or we could have groups of 2, groups of 3, things like that. But what if at least 2 people didn't? What if it's not at least 2? How many people would have purchased the same drink then? You might think 1, but that doesn't make sense. One person can't purchase the same drink there's nothing there because there's only one person. So if at least 2 don't purchase the same drink, that means that nobody purchased the same drink. So that would be the complement. Everybody got different drinks. So we could have this probability we're looking for is going to be 1 minus the probability that everyone got different drinks. And finding what everyone got different drinks, we can set that up. We've done this. If they're all different, the first one, well, they all had 8 to choose from. The first one actually did have 8 to choose from because he was the first one in line. The second person only had 7 because he had to get a different drink. So this one had one, so there were 7 left out of the 8 total. and then 6 left out of the 8 total, and then 5 out of the 8 total, 4 out of the 8 total, and 3 out of the 8 total. And so, multiply these together, that's the probability that everyone got different drinks. Notice this is an and situation. This isn't or. They threw complements here. This is what we were doing yesterday. So, we can multiply that together to get 0.0769, and then just go 1 minus that will be the probability that at least 2 people got the same drink. So 1 minus the 0.0769 is 0.9231, is the probability that at least 2 people got the same drink. This is, of course, assuming that it's completely random, they weren't watching each other, things like that. And so, that would be compound events. Again, it's stuff that you've been doing for the most part, but we're looking at it, and I will see you in class.